When we talk about engines, we often want to know something about the size of the engine. How do I quantify how big an engine is or be able to compare one engine to another? And there's a couple different metrics that we use, and that's what we're going to look into right now. Particularly, we're going to look, first of all, at the displacement of an engine, and we're also going to talk about the compression ratio, those two quantifications. So let's start off looking at an engine, and this is a piston, a drawing of a piston. And you see I have this piston in two different locations. You see then the left side of this figure, the piston is all the way at the top, as high as it can go. That's its maximum. So the crank down here that rotates around, that crank is at its highest position right now. And this, you see I have this labeled as TDC. This position we talk about top dead center. So the crank is at its very top, as high as it can possibly go. And that's where we say that is top dead center, top of the crank. Now, when that crank rotates on around and it comes down, it's going to pull this piston down. As it pulls it down, it's going to go all the way to the bottom here. And so this position where we have the crank at the bottom, we have this labeled as BDC, which stands for bottom dead center. And sometimes we'll actually see this called crank dead center as well, CDC. So either bottom dead center or crank dead center. So that is at the bottom. The crankshaft, the crank part of that crankshaft is at its very minimum. So if you think about this piston and visualize it, this is as high as this piston is ever going to go. This is as low as this piston is ever going to go. So that piston goes back and forth between those two positions. Now, when we talk about the displacement of an engine, the displacement of the engine is, by definition, how much gas by volume is displaced every time those pistons go up and down. What does that mean? Well, let's look at this. I'm going to draw a line between these two figures up here, between these two pictures, so that we can start to understand this. And I'm going to draw a line from the top of the piston at top dead center across the other one. So you can see this is as high as that piston would go. This is as low as it would go. The displacement of an engine is the volume that is displaced as the piston goes up and down. It's this volume right here. So it's the amount of gas by volume that piston pulls in every time that we have an intake stroke, and how much it pushes out every time we have an exhaust stroke. It's that volume, what comes in and what comes out. So I'm going to crosshatch this area. So looking at the side of this piston, this area that I have crosshatched here, this is the displacement of that particular piston. Okay. Now, one of the things we have to realize is that displacement doesn't have anything to do with the volume that is left above that piston. So when the piston is at its top dead center, it doesn't go all the way to the top. It doesn't actually hit the top of that combustion chamber. There's some space in there. And this space is independent, does not count in that displacement of the engine. Now, we actually have a name for that. So this area that's up above that piston, we call the clearance volume. Clearance volume. And that's going to become critical to us in a little bit when we start talking about the compression ratio of the engine, because that's going to have something to do with the compression ratio. But it has nothing to do with the displacement. The displacement is just basically how far the piston moves and how much gas that it will expel, either bring in or push out. And so it's this cross-hatched area as we're looking at the side of that piston. Now, let's think about this. What does that volume look like? It's a volume. We're looking at a two-dimensional drawing here, so we kind of see the side view of that volume. What does that volume look like? Well, if we could look at the top, get up above that piston and look down on it, most of the time those pistons are a circle. Almost always they're a perfect circle or near perfect circle. So I'm going to draw that and kind of put some dimensionality to it. So I'm going to kind of draw that here. Draw a circle that we're looking at from the side. That's what I'm seeing on the top of that piston, and I've kind of drawn it from an angle because we're going to see it's a view. Now, that's the top of this volume here. The volume then has some height. So what it's going to look like is a cylinder. So if I can draw that something like this, that displacement is going to look something like that. It's going to look like a cylinder. And again, this is the open space that is displaced by this piston as the piston goes up and down. Again, I can't emphasize this enough. This does not include the clearance volume up here. So we're not looking at the dimension all the way up to the top. We're just looking at the dimension up to here. So now, to get that volume, we need the volume of a cylinder. Oh man, how do we get the volume of a cylinder? Well, if that was a cube, that would be kind of easy. We'd do length times width times height, and that would give us the volume of the cube. But how do we do a cylinder? Well, we have to look at that circle on the top and get the volume of the circle and then multiply that by the height of that cylinder. So what is the volume of a cylinder? The volume is equal to the area of a circle, and if you remember the area of the circle, it's that pi r squared equation formula that we may remember from way back when. So the volume of the area of the circle is that pi r squared. That gives me the area of the circle, so to get the height, I need to know the height of that cylinder, so I'll multiply that by its height. So over here, this would be the radius of that cylinder. So if I'm looking at this little arrow there, that's my radius. And then this dimension is going to be my height of that volume that is in there. Okay, so radius and the height, that's the volume that gives me the volume of that gas, of that area, of that chunk inside on the top of that piston in there. That's my displacement. Okay, now let's do a little bit of algebra on that, because we don't often use a radius. We often will use a diameter. So the diameter goes all the way across these two things. So we can actually rewrite this as pi times a radius is the diameter, is half of the diameter. So we could actually rewrite this as pi times d over 2, the diameter, half of the diameter, so d over 2, and that term is squared because we have the radius squared, times the height. Now, a little bit more algebra. So we have that pi d over 2 squared times the height right there. So 2 is in the denominator, the 2 is squared, the 2 becomes 4, so that becomes a constant that we can pull out front. So we can rewrite this as pi times the diameter, pi over 4, times the diameter squared times the height. Okay, so that is my equation for the volume of a cylinder. So we can either do it with the radius of the cylinder, like we have up here, or we can do it with the diameter of the cylinder, like we have here. Now, let's extend this into some terminology for our engines. We have some specific terms that we call these dimensions, this height and this diameter of the piston. So if we look at this dimension, and I'm going to draw this dimension across here, so the diameter of that piston right here, the diameter of that piston, we call the bore, B-O-R-E. So that's the bore of that piston. Then this dimension, how far the piston moves up and down, we call that dimension the stroke. Okay, so the bore is the diameter, the stroke is how far it goes up and down. And that is exactly correlated to this cylinder that we have over here. The stroke is the height, how high that cylinder of gases is, or space up above that piston. And the bore is the diameter of this piston, or twice the radius of that piston. So we can actually rewrite this equation now to get our displacement. So our displacement, DISP, is equal to pi over 4, taking from this volume equation right here, times our diameter, which we said in engine terminology, when we're talking about engine, that is our bore, and that is squared because the diameter is squared, so it's pi over 4 times the bore squared times the stroke. That becomes the displacement. Now, I'm going to add one more little piece to it, because this is the displacement if I have one piston, if there's only one piston in that engine. Now, if I have an engine with multiple pistons, say 4 or 6 or 8 or something like that, I have to calculate the displacement of one of those pistons and then the displacement of the engine. I need to multiply that by the number of pistons in that engine. So there's one more piece on here. I'm going to say this is times a capital N. I'll use a big N for the number of pistons that we have in that engine. So that's the equation, that's where it comes from, and that's what it is. It's important that we understand what that displacement is physically within that engine and as well how to calculate that. So let's do a couple quick examples here of calculations. Use that equation to calculate some displacement related numbers. So here's my first example that I'll give you. It asks us to find the displacement of a two-cylinder engine. Okay, there right away. So there's two pistons in this engine, a two-cylinder engine, that has a bore of 3.54 inches and a stroke of 2.6 inches. Find the displacement. What's my equation? Let's write my equation down. My equation is the displacement is equal to pi over 4 times the bore squared times the stroke times the number of pistons. So displacement, pi over 4, bore squared, stroke times N. Now let's plug some numbers into. So this is into this equation. So this is equal to pi over 4. What is my bore? So if I look at my question up here, my bore is 3.54 inches. So I take pi over 4 times 3.54. And in my equation, that has to be squared. The next thing is the stroke, and I see from the question up here that my stroke is 2.6 inches. So I multiply this by 2.6. And then I've got to multiply by the number of pistons. How many pistons do I have in this engine? We said it's a two-cylinder engine, so I multiply this by 2. And now it becomes a calculator problem. So I pull out my calculator. I take pi times 3.54 squared times 2.6 times 2. Divide that by 4 because we have a 4 in the denominator over here. And that's going to tell us that our displacement is 51. Now, I've kind of left something off on this equation. So I didn't put any units in there. 51 what? What is that? Okay, so we should always keep our units when we're going through this equation. So what are my dimensions here? 3.54 was what? 3.54 was an inch. So I should have written that inch in there beside the 3.54. I'll just stick it in the bottom there for now. That goes with it. The 2.6 was also an inch, so I write that in inches. So what is my units coming out there? Well, let's look at this. 3.54 inches I had to square, so this becomes inches squared. And I multiply that by another inch, so I had 1 inch here, I square it, that gives me 2 inches. I multiply by one more, that's 3, so that is inches to the third power, or inches cubed. So this is 51 cubic inches. That is my displacement of that particular engine, 51 cubic inches. So again, keep track of those units. Don't forget about those units, or you get out to the end and you write that number down and then you wonder what it is and then you guess at it. So we keep those units in there, and that tells us that we have a displacement of 51 cubic inches. And that's it. It's a plug and chug. It's a pretty simple equation to work with. Just watch your units. A lot of people will forget this N, forget the number of cylinders in there, so don't forget to put that in there. And don't forget to square this bore. A lot of people sometimes will forget to hit the little square button on their calculator when they calculate that number. Our second example is a little bit different. So in this example, you're asked, how long is the stroke of a single-cylinder engine that has a displacement of 165 cc's and a piston diameter of 68 mm. Okay, so what's going on? A couple things. Well, first of all, we're kind of backwards. We're actually given the displacement of the engine this time, so we're told what the displacement is, and we've got to calculate the stroke. So right away, there's probably going to be a little algebra involved to rearrange that equation so that we can calculate what we need. The other thing that's a little bit different is our units are a little bit odd. So we have 165 cc's. What is a cc? Well, a cc is SI units, and it stands for cubic centimeter. So I'll write that down here so we remember that. That is a centimeter cubed, a cubic centimeter. And again, this is common terminology that you might see in literature or something like that. So I want to introduce it and make sure we all understand what this means. So you'll commonly see dimensions of engines in cc's or cubic centimeters. The other dimension that we have over here is our piston diameter. So our piston diameter, which is the diameter of the piston, that's the same as our bore. But that bore, the piston diameter, is 68 mm. What is an mm? That's a millimeter. And a millimeter is smaller than a centimeter. So there's 10 millimeters in a centimeter. So I could actually rewrite this as 6.8 centimeters, since there's 10 millimeters in a centimeter. So a couple different terms there, different units that we got to start getting used to so we make sure we understand that. Okay, so let's attack this problem now. Let's write down our equation. So our equation is the displacement is equal to pi over 4 times our bore squared times our stroke times the number of pistons that we have. Now, I have the bore, I have the displacement, I need to calculate the stroke. So how do I do that? Oh, I've got to solve this equation for stroke, so I can plug that in. So it becomes a little bit of an algebra problem. So basically what I have to do is move all this stuff other than stroke over to the left side of the equation. The way we do that is multiply both sides of that equation by the inverse of all this stuff. And what that will do is cancel everything out on the right-hand side, end up with all that stuff on the left-hand side of the equation in the opposite end, or either in the denominator or the numerator. They'll get switched over in there. So basically what's going to happen in here is that our stroke is going to be equal to the displacement was on the right-hand side of that equation, so the displacement stays there. The 4, we have pi over 4, so the 4 and the pi go upside down when they go over there. So this is going to be 4 on the top and pi in the denominator. So the 4 over pi go the opposite way. The stroke is there. The bore was on the top, so the bore is now going to end up on the bottom. So we have bore squared. And we also have the n on the right-hand side that's going to end up in the denominator. So this is what our equation looks like. Stroke times is equal to 4 times the displacement over pi times the bore squared times n. Now we can just plug numbers into this. So this is equal to 4 times our displacement is 165. And I'm going to write out cm cubed rather than cc, so we keep track of how many of these length units that we have. Divide that by pi. Divide what else is in the denominator? The bore squared. The bore is the piston diameter, and that's 6.8 centimeters times the number of pistons. And how many pistons do we have in this problem? Well, it's a single cylinder engine. It says up here in the problem. So that is a 1. So I'll write the 1 down there, but it obviously isn't going to mean anything. So calculator, how do I do this? To calculate this, I just basically take 4, put in my calculator 4 times 165 cubic centimeters, so 4 times 165 divided by pi, divided by the bore. Now I forgot to square this, so let's make sure that we don't lose that square down there. So divided by pi, divided by 6.8 squared, divided by 1, which doesn't matter. And if you run that through your calculator, you're going to find out that that stroke is 4.5. That's the number, but what's the units? Okay, let's take a look at this equation. What do we have? In the numerator, we have cubic centimeters because the bore is the displacement is a volume, so that's a cubic centimeters. In the denominator, we have 6.8 centimeters, but we squared that. So what we have here is a centimeter squared. So a centimeter cubed divided by a centimeter squared, you subtract those exponents, so that becomes 3 minus 2. So you're going to have 1 centimeter left in the numerator. So this becomes 4.5 centimeters. And that's how you calculate that. Okay, so again, a couple things, a little bit of algebra there that we got to work with. Got to remember not to forget the squares. I almost did when I did that example, so you got to make sure that that square stays in there. Pay attention to those units, especially sometimes if you've got a problem like this where you get units that are a little bit different that are mismatched. So if I would have just taken this 68 and plugged it in down here, I would have a completely wrong answer. So I got to make sure that all my units match together, they cancel correctly and everything. But that's how you calculate, that's how you use this equation. In this particular instance, we were using the bore and the diameter to come up with the stroke.